Good evening. Are you bored? Are you looking for a project for those long winter evenings, perhaps? Well then, this time, we have something that will satisfy your curiosity and your sense of adventure. So, let's start tonight's episode on building a single-digit VFD display on the Technomora channel. And here is a quick view of the complete circuit working. As you can tell, the VFD tube is lit up completely. I don't know why my camera refuses to focus, but I'm sure you can tell that the VFD is lit. Well, there you have the whole circuitry that's powering it, finished on the breadboard. We still have to transfer it to PCB, and over there you can see the filament voltage that I'm pumping through the filament. It's almost 1 volt DC, by the way. Okay, so actually, yes, as you can tell, the room is lit, but even with a lit room, the VFD is pretty bright. I was curious to see how much current the whole VFD driver circuit would consume while the VFD is on. Now, I didn't switch on the complete VFD, but only half of it, because I think there will never be more than 4, let's say, segments on at a time on average. So with the filament set to 1.1 volts, so let's say the maximum recommended for the filament, how much does the whole circuit consume in current? Well, let's have a look. There you have it. It consumes at this moment 91.2 milliamps of current. 91 milliamps of current. Not too bad, considering that the whole circuit powers not only the filament of the VFD, but also the DC-DC converter and the anodes of the VFD tube. Now, keep in mind, of course, this is only for one display element. If you're going to drive 4 of them, well, then you'll have to multiply it by 4, which would make 364 milliamps, which in turn would mean that if you're going to drive this via the power supply of whatever apparatus you're going to build in your VFD tubes, you need to take into account the power supply must be capable of supplying at least, for 4 VFD tubes of that type I'm using right now, 360 milliamps extra. So that's quite a chunk of current extra the power supply has to be able to deliver without burning up, obviously. The filament power supply for the VFD tube looks pretty much, schematically speaking, like this. Okay, so you have basically in an NPN transistor which in my case is a BC547, which can be brought into conduction via a voltage divider, which you see here, consisting of a potentiometer and a fixed resistor connected to the base of the transistor. And what you basically do is you make the transistor conduct more or less, which in turn passes either more or less voltage from the power supply through the collector, through the emitter and out to whatever you want to power with it, which in this case of course is the filament of the VFD. Now there is one detail that you'll notice, and that's the NTC here. The reason why I placed an NTC on the output of the power supply, the variable power supply for the filament, is because you see, when a filament is cold, it has far less resistance than a hot filament, which means that if you connect it up to a power supply, initially it will draw a lot of current. So you will get what they say, or what they call, an inrush current. And that kind of inrush current is not very healthy for a filament, okay? So you should try to avoid that, because it tends to overheat for just a very short time, so it won't necessarily burn through, I mean the filament, but if you do it many times, on and off and on and off, you will in the end up by damaging the filament a lot more. So in effect what happens is that initially this NTC here has about 100 ohms resistance, which means that the current flowing through the filament is initially low, and as the NTC heats up, because there's a lot of current running through it, its resistance drops, which in the end of course allows more current through to go to the filament. Let's say it just gives a filament an easy, slow start up. Okay, I just wanted it that way because I wanted to spare the filament of my VFD tube. And anyway, this happens only once. Okay, so when you switch the VFD on from cold state, then this of course will kick in. But that's about it. Now here you see the parts needed to build the little power supply for the filament. Now I should tell you that once the power supply is running and the filament is glowing, well, is hot, the transistor you see here will also start to run hot. And when I say hot, I mean you won't burn yourself if you touch the transistor, but it will feel very uncomfortable. So it will be so hot that, well, it will be painful. Yeah, but you won't hurt yourself, but, well, not permanently, but it'll be very uncomfortable. So I guess the transistor will heat up to somewhere around 70-75 degrees Celsius. So if you want to avoid that, you could switch to another type of transistor, which is a BD 139. That transistor can dissipate a lot more heat, and it can handle quite a bit more current too. So it won't run as hot as the BC547. But, you know, for the sake of simplicity, I used only BC547s in my design. It's up to you. If you want to use a heavier type of transistor, like an NPN transistor, like a BD 139, that's up to you. I'm in the process of transferring all the parts from my breadboard to little perf boards like you see right now in the image. So these are the other parts of the design. So right at the top, let me see if I can zoom out a little bit. So right at the top, right here, what you see here is the voltage multiplier. And as you'll see in a minute when I explain how all the parts, the separate parts, are designed, you'll see why it has so many capacitors. And right underneath the voltage multiplier, so this part right here, is the oscillator. For the people who are used to high frequency stuff, it is a Colpitts oscillator. Well, a slightly modified one, but basically it is a Colpitts oscillator. And then the little part you see in my gripper tool over there, so at the top right of the image, that will be the variable filament power supply for the VFD tube. As you know, VFD tubes are particularly sensitive to the amount of voltage you send through their filaments. Basically, a VFD doesn't take more than a volt. Yes, exactly 1 volt through their filament. So if you send more than 1 volt through the filament of a VFD, it won't make that much of a difference to the brightness of the VFD. And basically, if you send more than 1 volt through its filament, you'll burn the VFD very, very quickly. You know, if you drive it like a filament light bulb, well, you can count on it that it'll be burned up after an hour or so. So, since the brightness really isn't that important, I mean the filament brightness of a VFD, you can send less than 1 volt through it. And experimentally I noticed that if I send about 950 millivolts through the filament, that's more than enough. In fact, the filament of a VFD, it's a little bit of a misnomer, okay? It's not actually a filament, it's more like you could say a very primitive electron gun, nothing more than that. So yeah, there you go. And for the people who don't actually know what a VFD tube is, I mean the principle of a VFD tube, I would say, aside from the fact that it's built differently from an old-fashioned CRT tube, you know, those old picture tubes in old TV sets, the principle is more or less the same. So you have a filament at the back which sends electrons forward to the front of the tube, so the part of the tube you're seeing right now, and those electrons hit small targets, which in this case are formed like the digits of or the parts of a digit. Okay, there are 8 anodes, in fact, you can see here if you count those. And those targets are covered in phosphor, and if you hit the phosphor with enough electrons, the phosphor will start to glow. In this case, they will glow a greenish kind of color, very, very slightly blue, but overwhelmingly green, let's say. And the only thing you really need to do is to focus the electrons onto the phosphorus layer. And you do that by turning the phosphorus targets positive with, relative to the filament, reasonably high voltage. So I would say anywhere between 15 and 30 volts will attract enough electrons to the phosphorus anodes to make them glow. Okay, and in between the anodes of the tube and the filament there is a grid, a kind of grid. Okay, and that grid you can bring under a certain positive or negative tension, and depending on the kind of voltage you send through it, so either a positive or a negative one, you can either suppress any glowing from the digit anodes, so in essence turn off the tube, or if you turn the grid slightly more positive, you can make the anodes glow either very faintly or very, very brightly. So in effect the grid is a sort of an electron suppressor in one case, so if it's negative, or an electron gun, in fact, so an accelerator if you make the grid positive. Now, just to be clear, what I said about the filament goes for the anodes as well. I mean, you could go completely overboard and send, I don't know, 100 volts DC to the anodes, and that would certainly make them very bright, but it would also burn them up in a flash. Okay, so you really need to find a sort of a, let's say, the Goldilocks area where it glows just enough to be legible, but not so bright that you would burn it up in a flash. Okay, so like I said, I'm transferring one by one all the parts I built to little perf boards like you see in the gripper. So over here, this is the filament power supply. Okay, and as I transfer them to little perf boards, I test them. So once the little filament power supply is done, we'll give it a test. To power the anodes or the segments of the VFD tube, we need to have high voltage. Now, since I'm using only one power supply, or well, in my case a battery, I need to find a way to easily pull up voltage to the necessary level to make the anodes glow. Now, the way that's done actually is by inputting AC voltage on this side of the voltage multiplier and then collecting the multiplied input voltage at the output right here, and that obviously will be DC voltage. Mind you, with quite a bit of ripple on it, but still quite usable. Okay, now if you're going to input, say, 9 volts AC, so 9 volts peak to peak AC into the voltage multiplier, the multiplier will only actually use half of it, and in this case only the positive half of it. So if you input 9 volts AC, that means it will only use 4.5 volts effectively, and since there are in this case 5 stages, each stage being symbolized by a diode, you will multiply it by 5, giving you, theoretically at least, 22.5 volts DC at the output. Now, mind you, you would be lucky to get 22.5 volts, since each of these diodes consume a little bit of voltage on their own to be able to conduct. Okay, so you'll never get the theoretical voltage at the output, rather let's say 2 or 3 volts lower than that. Okay, so like I said, if you use high quality diodes, you might get away with only a drop of 2 volts or so at the output, but that will largely depend on the quality of the diodes. Now, building this voltage multiplier is, as you can tell from the schematic, is really not very difficult, and you only need 5 diodes, and I used 1N4007 diodes, which are extremely common, and I used 5 capacitors, 5 electrolytics of 47 microfarad, 50 volts. Now, there are 2 things to remember about this voltage multiplier. Okay, whereas it is a sort of a cheap way to pull up voltage to a much higher level, there is a catch. If you multiply the input voltage by 5, you will also divide the current it can source by 5. So if, let's say, theoretically you input 4.5 volts AC, you will get 22.5 volts DC at the output, but if you input 100 milliamps here, you will only get 20 milliamps here. Okay, so 5 times less current here. So yeah, you have to find, let's say, the right compromise, the compromise that will work for your design. Okay, so I'm soldering the transistor to the little perf board, and I just wanted to show you how I do this, and in essence you'll notice that each perf board I cut for the project is a little rectangle, a rectangle, and the point being that each rectangle will be stacked on top of the next one with little standoffs. I don't know yet if I'm going to use metal or plastic standoffs, but the idea is to keep each PCB, let's say, a bit away from the next one. So these are in fact all the other PCBs, okay, I cut. So, and you'll notice little holes I drilled inside of them. Okay, so these holes will be obviously the spots where I will use screws or standoffs themselves to, well, to mount one perf board on top of the next one. Okay, so that's the whole idea, in fact. So okay, we soldered the transistor to the perf board. Nice solder points, rather clean. Yeah, I'm not too displeased with it. So another detail you'll notice is that I made a sort of a little, well, ugly looking heatsink to my transistor. Okay, I used for that copper tape. Now the reason for that is that although the transistor, if you read the specifications of a BC 547, is rated for dissipating 500 milliwatts of power, I am not so sure that it can do that without a little bit of help. So I effectively doubled its surface area by sticking to it some copper tape, and hopefully that will help the transistor dissipate a bit more power. Yeah, so because at peak it will probably have to dissipate, I'd say around 200 milliwatts, and that will make it already pretty hot. So any help the transistor can get, I reasoned, is good. And since I can't hardly mount a fan on top of this, I made my own little heatsink. Okay, so let me solder on a few more parts and I'll show you the result. Well, there you go, all the parts are mounted. Okay, so I tried to squeeze them, as it were, in the upper left corner of the little perf board. The reason being that the filament power supply, which you see now in the center of the image, will have to share the perf board area with the high voltage power supply for the anodes of the VFD tubes. So basically this area here, so here to here, all of this will be used by the high voltage section of the power supply of the VFD tube, and really that entails all those capacitors you see over there. So all of these, so 4 of these and 4 diodes. Okay, so all of this will find a spot right here, in fact. Okay, so that's where they'll all be well, mounted. And let me show you the reverse side of this so that you get a better idea of how I mounted it. Okay, so, well, as you can see, all the parts are soldered, and I did leave a few leads still on. So normally, of course, I cut away all the leads that I don't need, but I did leave a few leads still present on the board. And the only reason for that is that, like I said a minute ago, once the board is completely assembled, I always tested just to see whether it works normally or not. And if I leave a few of the leads hanging on like they do right now, that makes measuring voltages so much easier for me, you know, because then I can use little clips like this, for example, little gripper clips like this. Just need to hook them around the lead, and there you go. I can measure right away voltages, resistances, anything. Obviously, I don't leave all the leads sticking out, but the leads I know will carry important signals or important voltages. I do leave hanging out like this or sticking out like this for a while, just for testing purposes. Once I know the board works perfectly, I just cut them away, and that's the end of it. Okay, I should tell you that this is an ongoing project. Okay, so anything I do to the circuit as it is right now is experimental, meaning that I might still make some tweaks to the design to make it work better. And I made exactly 2 tweaks to the circuit up to now. So right here you see the filament power supply, okay, this little part here, and you see the voltage multiplier ladder over here. Now the tweak I did to the filament supply is that I built in an NTC so that the inrush of current into the filament of the VFD is not so, let's say, not so intense, thus sparing the filament a little bit, so not putting immediately a huge amount of current through it. And then the other tweak I made is that originally I had a quadrupler here, okay, so meaning I multiply the input voltage, AC input voltage, by 4. I actually made it a quintupler, okay, so a 5-stage multiplier, meaning that the AC which I input into it is multiplied by 5 times to DC on the output. Now it's not entirely 100% like I say it right now, but explanations will follow, don't worry. Okay, so let's see what both tweaks had as an effect if I switch on the VFD. So here we go. One moment. Yeah, there we go. So as you can tell, the VFD slowly starts to glow. Okay, so it takes, say, 5 or 6 seconds for it to glow really brightly. Now you'll notice I didn't connect all the anodes of the VFD, okay, so this is just for experiment purposes. So anyway, as you can tell, the VFD glows really bright, even with the light coming from the camera. Okay, so maybe I can even make a close-up. There you go. So yeah, the VFD is extremely bright now, which is good. And well, as you could tell a few seconds ago, the VFD comes up very slowly. Yeah, it takes, say, 5 or 6 seconds to come to full brightness, and that's exactly what I wanted. That's the effect I wanted to reach with building in an NTC into the design rather than a permanent resistor. And the NTC, let me show you. The NTC is that little green thing over here. Okay, so let me zoom out a little bit. So the NTC is that green thing here. It still gets pretty warm once the VFD is running at full power, but don't worry, the NTC can take it. Okay, so the transistor gets warm as well. I would say if you touch it, uncomfortably warm. You could put your finger on the transistor and keep it there, but it would hurt after a while. You wouldn't get scarred or damaged by it, but it would certainly be very uncomfortable. So my guess is the temperature of the transistor must be somewhere around 70 degrees Celsius, something like that, which is pretty warm to the human skin. Okay, so anyway, there you go, and there is the quintupler, as I call it. So you see, if you count all the diodes that form the ladder, yeah, if you count them from left to right, you'll see that there are 5 diodes, and it's easier if you just count the capacitors. Okay, there are 5 capacitors, meaning there are 5 stages to the voltage multiplier. So yeah, the 2 tweaks I made seem to be satisfactory. So what I'm going to do now is I'm going to transfer the voltage multiplier you see here over to the little filament supply board. You see, I have a whole area on it which is free, and I'll build the voltage multiplier right here. There you go. So I hooked up the voltage multiplier to my multimeter, which you see in the image right here. Let me see if I can set it up without too much reflection on the screen. Okay, so I'm monitoring the output of the voltage multiplier. Now, the voltage you see on the screen is residual voltage that was still inside the capacitors you see on the voltage multiplier. Okay, so it's just the capacitors, the row of capacitors you see here, discharging themselves through my multimeter. So the voltage multiplier is connected to the Colpitts Oscillator setup, which you see here, and which produces the sine wave AC we send over there, yeah, to be transformed into DC. What I'm also doing is I'm monitoring the output of the Colpitts Oscillator on my oscilloscope, just to see whether it is oscillating or not. So what I'm going to do now is show you what happens when I power the circuitry via this lithium-ion battery. Okay, so it's a 7.4 volts battery which I will connect up to the Colpitts Oscillator. So let's just do that and see what happens. Okay, so let's see if I can give you a good angle to see most of it. So unfortunately I don't think you will see me connect up the battery, but there you go. Now you see the multimeter and the voltage doubler or multiplier right here. So here we go. Let me just connect it up and keep an eye on the meter. There you go. You see it almost instantly rises to 19.3 volts, something like that. Yeah, it's holding at 19.3 volts. Now, the reason why I built a quintupler, so a voltage multiplier that multiplies input AC voltage by 5, has several reasons, but let's say there are two main reasons why I did it in the end. First of all, having a quintupler allows me to use DC power sources for the whole electronic device, ranging from between 5 volts DC up to, let's say, 12 volts DC. Since the voltage multiplier only uses the top half of the generated AC, you have to take into account that, say, if you use 5 volts DC to power the Colpitts oscillator, you'll only be effectively generating 2.5 volts positive, yeah, AC I mean. If you want voltage which is high enough to fire up a VFD, you need to pull up the 2.5 volts to above 10 volts DC. Okay, so if you input 2.5 volts AC into the voltage multiplier by 5, that would mean let me see, 12 volts and a half output, which is pretty low. So the VFD will still light up, but it'll be, well, rather faint. You'll still be able to see it, but it won't be very bright. However, oh, damn multimeter. Okay. However, if you input, say, 9 volts DC, then about half of the generated AC will be 4.5 volts. If you multiply that by 5, you get, let me see, 22.5 volts. And 22.5 volts is decent. If you use that, the VFD tube will light up quite brightly. It'll be really bright and easy to read from. Now if you go to 12 volts DC, that means the top half of the AC will be about 6 volts. If you multiply that by 5, you get 30 volts. Now you have to remember that the VFD tube is, or rather the anodes of the VFD tube are rated for anywhere between 20 volts DC and 30 volts DC. If you're going to inject more than 30 volts into the anode, it will still light up. In fact, it will light up extremely brightly, but it won't last very long. You see, because that's why they give maximum ratings for things like that. Okay, so the manufacturer of the VFD tube tested his tubes and just simply saw empirically that if you inject more than, say, 30 volts DC into the anodes, it'll burn up rather quickly. And I'm using the term burn conspicuously here because it will effectively burn the anodes. So yeah, the quintupler allows me to generate voltages, high voltages, relatively speaking, of course, for the VFD tube. And it allows me to generate those high voltages with the help of a simple battery. Okay, so I'm using a 7.4 volt battery right now, and well, as you see, it's still working perfectly. Yeah, there's a bad contact somewhere. I haven't found it yet, but then again, who cares? Okay, I mean, this is only a temporary setup. I'm going to transfer all the parts you see here to a small PCB, and in fact that's what I'm going to do just after I show you the AC that comes out of the Colpitts generator. And you see it over there. Okay, let me zoom in. Okay, there you go. So that is the sine wave that I pump into the voltage multiplier. Now, the more astute among you will notice that the bottom part of the AC is flattened a little bit, and that has to do with the capacitance of the voltage multiplier. Okay, as soon as I connect it up to the AC, it flattens a tiny little part of the sine wave. Yeah, I guess it's an impedance mismatch or something like that. I haven't quite figured out how to remedy that yet, but actually I'm not going to spend too much time trying to figure out why the negative portion of the sine wave is being flattened just a little bit. And the reason is very simple. Since we only use the top half of the AC, so anything you see above the screwdriver rod is what we'll use, and what comes below it will simply be ignored. So I can safely ignore anything below the screwdriver. Okay, so yeah, I'm not going to spend too much time on it. I might, out of curiosity, once the whole thing is done, try to tweak it maybe a little bit and see whether I can perfect, let's say, the AC wave that comes out of it. But really, it's not very relevant to what we're trying to do. So there we are. Next step is to transfer the oscillator you see down there on the breadboard to a small PCB. So something like this. Okay, so the oscillator circuit is built, or if you prefer it, it's transferred from the breadboard you see down here to the PCB up here. Okay, and we're going to test the connection between the sine wave oscillator and the high voltage converter up here. Okay, so this is the voltage multiplier I built. You remember the quintupler, and it's connected to the output of the oscillator. I attached my multimeter to it. I don't know if I can combine both, but let's see. Okay, there you go. So I'm monitoring the voltage on my multimeter, and I think you can just about see it. And what I'll do is I'll connect my lithium ion battery to it, and then we'll monitor together the voltage that the voltage multiplier outputs. Okay, so here we go. And ta-da. 3, 2, 1. There you go. And you see the voltage immediately jump up to 19.97 volts, so almost 20 volts DC. Okay, so, and that's what the circuitry you see in front of you is generating. Now, mind you, as impressive as this may sound, the 20 volts DC will drop a few volts. I would estimate 5 or 6 volts once it's attached to the VFD. So this is voltage, DC voltage with no load, okay? Absolutely none. And if you're curious about the waveform of the AC which is being pumped into the voltage multiplier, have a look at that. So that's the AC I'm pumping into the, well, you could say the voltage converter. Okay, so let me see. The AC measures peak to peak 1, 2, 3.5, and we're at the 2 volts setting per division, so that would be 7 volts, which is quite close to the voltage of the battery actually. Okay, so let's see about the frequency now. The frequency is, let me see, the frequency is, well, pretty close to 57 kilohertz. Yeah, 57 kilohertz. Okay, well, 56.8 actually. So the frequency changed a little bit from what we measured before, because I am using another set of capacitors for the oscillator. You see here, I use tiny mylar capacitors which I had in one of my drawers, and obviously they slightly differ in value from the original ones, well, the ones I had used on my breadboard, you know, these safety capacitors. Okay, so instead of these I'm using regular mylar capacitors, the brownish ones you see over there. Okay, so, well, I'm rather pleased that it all works. So now that we know that the transferred filament power supply works, we know the voltage multiplier works and the oscillator, well, the next thing to try is to see whether a VFD tube will power up normally when connected to these. What do you think? Let's see. Well, there you go. The circuitry is connected. You see a whole bunch of crocodile leads, all leading up to the VFD tube, and the VFD tube is powered from it, and you can still see the VFD quite clearly, even though my camera is shining on it with a little spotlight. Okay, so but that's because there's a little bit too little light. Let me switch on. Voila, a bit more light, like that. So there you go. That's the VFD powered with the circuitry which I transferred to the two small PCBs you see over there. Only two more things to do, which is to build a small, you could say, video control board. So a tiny board with which we will control the anodes on or off, and well, then we have to connect it all up. So all the separate little boards which I've made up to now, and the little video control board which I'm going to build in a moment, and the VFD tube, they all need to be connected up. To be able to use a voltage multiplier formed by a ladder of diodes and capacitors, electrolytic capacitors, you need an AC power source. Now, technically you could use, without any sort of problem, a small transformer, but since we intended to power the whole design with one power source, and moreover a DC power source, we needed to produce our own AC to be able to use the voltage multiplier. And the way I do it is by making an oscillator. And you see the schematic of the oscillator right here. In fact, you should look at this schematic as consisting of two parts, and you should see C4 as, say, the delimiter between this side, which is the oscillator, and this side here, which is an amplifier. Okay. This oscillator here is what is called a Colpitts Oscillator. Now, I'm not going to go too much into details about this Colpitts Oscillator. If you want to know more about a Colpitts Oscillator, you should go watch my episode on building an IF radio frequency generator. Okay, it's one of my other weekend projects which I uploaded to my channel. So go have a look there and you'll get all the explanation about a Colpitts oscillator. I'll tell you this much though. The Colpitts is really a very reliable, very stable oscillator, and its frequency is, in this case at least, is mainly influenced by these two capacitors here, so C2 and C3, and the coil you see here, L1. So if you use those three components in a formula which I wrote here, Whoops. So here, if you input all the values into this formula here, you can calculate what the final output frequency will be of the Colpitts generator. Now, mind you, this formula here, which is within the dotted line, is incorrect, okay? The reason why I wrote this formula is because I wanted to show you about what kind of values we are really talking. So over here you see the values expressed in Henry and Farad, whereas here I'm writing the values in the actual values of the components. But if you're going to calculate it, the formula with these values, it's never going to work, okay? It's just going to be erroneous. So I just wrote it down to show you what components are being used for the calculation. Now if you work out the calculation to the very end, you'll see that you'll get a frequency of 52.8 kilohertz theoretically. Now in practice I got frequencies anywhere between, say, 56 and roughly 58 kilohertz. And the reason why that is because the value of the components used is never quite precisely what you theoretically calculate, okay? There's always a little bit of divergence in your components. But let's say the formula at least gives you an idea of the frequency you're going to generate. Now again, I used very common parts to build the oscillator, okay? You see them there, and I use once more the BC547, okay? Now I'll add one more thing about the oscillator. Like I said, the oscillator in my design, in the VFD Tube display design, which I present to you today, there are two parts. So I told you this is the oscillator, this is more like an amplifier. And the reason why that is because you need to power the voltage multiplier with AC voltage and quite a bit of current as well. If you were to take the output of the oscillator right here where C4 is attached, that might work if you wouldn't need, more than, let's say, a couple of milliamps, and that's it. But you know, your coil would run extremely hot, yeah? The amount of current that would run through your coil would be in fact so great that your coil would even burn, yeah, or quite literally burn, okay? So you can't use the oscillator itself, unfortunately, perhaps, to drive the voltage multiplier. So what I do is I send the signal of the oscillator through a capacitor, so capacitor C4, and a voltage divider into the base of another transistor. And this transistor is being switched on and off with AC, yeah, but with a very small AC on this side, which produces quite a large AC on this side. And this side will supply virtually any amount of voltage and current the voltage multiplier needs. Well, I say virtually. It will never consume more than what it needs, of course, but this transistor might run a little bit warm, but that's it. If I would pull the current directly from the output of the oscillator, this coil would literally burn up, okay, because it isn't constructed to carry that much current. So that's why in this design at least you have actually two stages to the oscillator. That's about it. This generates all the necessary AC to power the voltage multiplier. I'm building the video control board, which you see there on my little stand. Okay, so I'll show it to you once it's finished. What I'll be doing the next few minutes is cutting a bunch of wires and connecting all the PCBs to each other and to the VFD tube you see there at the end. I think by now you are all curious to see whether the design will work, and don't you worry that all that over there is a little bit chaotic. I still need to finish it off completely, but you know, I'm understandably curious, and I think all of you are as well, to see whether the final design as I put it together will work. I made a little video driver board, you could say, which is the top one over there, and you see all the wires going to this crocodile lead. What I intend to do is to send a low voltage to all the video driver transistors on the top board, which will switch either on or off the anodes of the display. Now obviously if I send a voltage to all of the transistors, all of the anodes of the display will be powered and therefore should light up. So yeah, well, I connected up my design to my trusted lithium ion battery pack, and well, yeah, I'm going to switch it on by inserting the positive lead of my circuit into the positive lead of my lithium ion battery, and well, either nothing will happen, everything will happen, or we get a nice big puff of smoke. So well, here we go. Or I think, like the Americans say, here goes nothing. Okay, so let me give you a nice view of the VFD and the circuitry. Okay, so I don't have a drum, or I would give you some drum rolling, but here it goes. I'm connecting it up about right now. Oh yeah, it works. Oh wait, the top anode doesn't work. Let me see. No, it's okay. No, I bunched all the wires together. Okay, there you go. There you go. It works. Yeah, well, okay, the crocodile lead is a little bit of a temporary solution, but it works. Well, I'll be damned. Yeah, well, it took quite a while to assemble it and to design it and to try it out, but when you see the result of all your work actually working, I mean, that really gives a kick, let me tell you. Now, to switch an anode of the VFD tube on and off, you need effectively a kind of a switch. And what I use to do that is a single transistor for a single segment. Okay, again, I use a BC547, which you see here, and I basically use it as a switch. So if I send in a positive signal to the base of the transistor, it will conduct, and it will let through voltage through the collector and out through the emitter to whatever you want to power. In our case, of course, that would be the anode or the segment, one of the segments of the VFD display. Okay, so in effect you need one of these little circuits for each segment of the display. Since there are 8 segments, you will need 8 times this little circuit. Okay, and you only need 2 parts for it, so a transistor and a resistor, and that's it, nothing more. And a whole bunch of wires, of course, to make it, but basically it's really simple. So in here you will input any sort of positive signal you want to switch the transistor on or off with, and in here you will input the voltage which comes from the voltage multiplier. Okay, so that's important to note. Aside from that, like I said, it's really very simple. So it's either on or off. And here it is, completely assembled with the help of some plastic standoffs you see here. I think it's a 1-inch standoff I used. I need to have a look. It's possible that it was centimeters, so I would say a bit more than 2 centimeters. Okay, so I guess 1-inch standoffs, and there's a column of standoffs on this side, and there's a column of standoffs on the other side. I think you can just about see them over there, and that's how it is. That's how I intended to make it from the beginning. Granted, some people might say it doesn't look very aesthetic, but I would more or less disagree. I think, okay, it's not really beautiful, but aesthetically speaking, I think it looks nice as a design. It also shows how much peripheral hardware a VFD needs to function, which is quite impressive actually. If you look at it, the amount of electronics you need to make a well, to make a VFD light up first of all, but also to drive it, you know, to switch it on and off, or even, I suppose, making it glow brighter or less bright. Yeah, it does need quite a bit of peripheral electronics to make it work. But if you can make it work properly, like this one does, then it's really a pleasure to see. And actually, considering the fact that I used off-the-shelf parts and just some breadboard PCB, I think the result is really not too bad.